All righty. So here we go. The goal today is for you to understand two different types of transformations. Two different types of transformations. One's a dilation, one's a rotation. One's a dilation and one's a rotation. Okay? If at any point I'm using like terms where you're like, I'm not exactly sure what that means, you should ask. Okay? Let's start with the dilation. And we've already kind of discussed dilations a little bit when we got into scale factor stuff. But what does anybody remember what dilation is?
So where you change the size but not the shape?
It's where you change the size but not the shape. And in fact, if any of you have glasses or have been tested for glasses, you go in and you had your pupils dilated.
Oh, yeah.
And it's this weird thing when they put drops in your eyes and then you can't see for a while. It's all blurry and weird, right?
You're sensitive to light.
Yeah. You know why you're sensitive to light? When you have your eyes dilated.
Because your pupils grow really small, but your pupils are supposed to get bigger when you're
Yes. Because what those drops do is they open up your pupils. And what happens is it's like when you walk out of a movie theater. When you walk out of a movie theater, your pupils are very large because it's dark inside of a movie theater. And then you walk out in the bright sun, and it's why it hurts a little bit, because all of a sudden you go from dark to bright, your lenses in your eyes are opened up, letting all this light in, and immediately you're actually kind of blinded for a quick second until your pupils close up to restrict that amount of light coming into your eyes. Okay? What are we going to say, Libby? Yeah? Yeah, ask your mom. Teaching. Go away. Okay. Go ahead. And that's because when you close your eyes and then open them, they'll adjust themselves, right? A dilation in math is something that makes a shape larger or smaller, and it's done mathematically through the use of something called a scale factor. A scale factor makes something larger or smaller through multiplication. You may only use a scale factor with multiplication. So it begs the question, how do you make something larger through the use of a scale factor? Well, you can multiply it times any number whose absolute value is greater than 1. Absolute value.
You can't use 0.
Oh, well, yeah, because what would 0 do with it? Make it disappear, essentially. Yeah, if you ever use a scale factor 0, it would basically make the figure disappear because it would just go away. Absolute value, let's get an absolute value just really quick. The absolute value of 3 is 3. The absolute value of -2 is 2. Absolute value is the number's distance from 0. And distance can never be a negative number. You can't walk -40 feet. I'll give you just 3 minutes. Just sit. Okay? In other words, if I were to measure the distance from me to that wall, I would measure it. It would be at however many feet. If I were to measure the distance to the opposite wall, it wouldn't be a negative number of feet. I would simply turn and measure the distance. And it would be a certain number of positive feet as well. Absolute value is a number's distance from 0. More easily described, absolute value turns any number into a positive number. Absolute value turns any number into a positive number. Turns a negative into a positive, positive stays a positive. Okay? That's what we're going to say.
What about scale factors and fractions?
What about them?
But you said they have to have an absolute value of greater than 1.
No, I didn't. I said in order to make a shape larger, you would use a scale factor whose absolute value is greater than 1. Okay? And by the way, just because it's a fraction doesn't mean it's less than 1.
True.
Right. So you have to be careful about that, right? If I use a scale factor of 5/2, is my shape going to get larger or smaller?
Larger.
It's going to get larger because it is greater than 1. Okay? Now, in order to make a shape smaller, to reduce its size, we would just make sure we would want to multiply times the scale factor whose absolute value is less than 1. What is 1 going to do? Same size, right? if I use a scale factor of -1, if I use a scale factor of -1, what is my shape going to do?
Just reverse.
It's going to stay the same. It will be isometric, right? It will be congruent. It will be the same size. It'll be, oh, by the way, I did figure out the difference between congruence and isometry. Isometry refers to, I was thinking about that, I was like, they can't be exactly synonymous. They're not. Congruence refers to a side or an angle, a particular single measurement. Isometry is where you're comparing shapes, okay, with multiple sides. Yeah. So in other words, you can say that two shapes are isometric, but you wouldn't necessarily say that two shapes are congruent. You can say each of their sides is congruent, but you can't say that the shape is congruent. That's kind of the difference. But again, it's one of those terms that people screw up all the time. I hear people all the time say that two shapes are congruent, although they're really. Okay? Any questions on all that fun stuff? So a dilation simply makes it either larger or smaller through the use of a scale factor. Okay? Now, I will tell you that before we get into locations, which is the harder one, there is one thing, a lot of times you're going to be asked to find the scale factor. And I will tell you the easiest trick in the entire world to find the scale factor. Say we have a triangle whose measurements are 8, 8, and 5. So I'll mark those as such. And then I have a triangle that is 15, 24, and 24. And this is triangle A, and this is triangle B. And I say, what's the scale factor? It changes triangle A to triangle B. Alex, it is 3. Right? Because each side is being multiplied by 3 to get the next size. Agreed? Okay. So what happens if say I have this triangle, which is 6, 6, and
7.
Well, I'm going to do something less obvious.
Yeah.
So now I have triangle A, I have triangle B. And I say, now I just want you to listen. And I say, I want you to find the scale factor that changes triangle A to triangle B. It changes triangle A to triangle B. Now, I know some of you know, I just want you to listen, so I want everyone else to kind of understand this. The easiest way to identify the scale factor is to take the end number divided by the beginning number. You take the end number, the product, divided by the initial number. So basically what you would end up with is 4 over 24, which is 4 divided by 24. And 4 divided by 24 simplifies to what? It simplifies to 1/6. That is your scale factor. Because your scale factor is using only multiplication. Because some kids will go, well, the scale factor is divided by 6. No, it's not. Because there's no such thing as a scale factor that uses division. Scale factors only use multiplication. So you take the second number, divide it by the first number, and simplify it as a fraction. And that will tell you your scale factor. And if you think back to our initial one, where we ended up with 8 and 24, what's 24 divided by 8? 3. Scale factor.
What if they're all different?
Then it's not a scale model, is it?
Oh.
It's not a dilation. In order for it to be a dilation, it has to be the same number for all sides. Is it the same for this? It is, because 3 divided by 18 simplifies to 1 over 6. In order to be a dilation, every side has to be proportional to the other side. It has to use the same scale factor.
Wait, but do the two sides of the triangle have to be congruent?
No, I just made it that way.
So it could be a
It could be.
Yeah, this could have been, if we didn't have these, This could have been 30, and this would have been 5. Still a dilation, because every side multiplies by the same scale factor to get the other sides. Okay? Now, on a coordinate grid, the easiest way to do it is to find your ordered pairs and to multiply both times whatever your scale factor is, and it will give you your new ordered pairs.
How do you know your scale factor?
They usually give it to you. If they don't give it to you, they may give you this and this, then how would you find the scale factor? X divided by X will give you your scale factor. Okay? Yeah.
But if you multiply by scale factor, do you multiply each number like X and
Yes, you multiply the X and the Y by the scale factor.
How
Very
would you
good.
multiply 2 points on a grid?
Well, I don't know what that means.
You can't like multiply 4 times 3, 2. No, you multiply
Let's see.
4 times the scale
Watch. Here I have a coordinate grid, right? So I'm going to mark an object at 2, 2, negative 2, 2, negative 2, 4, and 2, 4. Right? And we're going to label them A, B, C, and D. Now A is at negative 2, 4. B is at 2, 4. C is at 2, 2. And D is at negative 2, 2. And I say we're gonna dilate this by a scale factor of 3. We're gonna dilate it by a scale. In fact, you know what? Let's dilate it by a scale factor of negative 3, just for giggle's sake. We're gonna dilate it by a scale factor of negative 3. That would make A prime 6, negative 12, right? Because I multiplied both things by negative 3. Okay, that would make B prime negative 6, negative 12. That would make C prime negative 6, negative 6. And that would make D prime 6, negative 6. Any questions about how I got those points? So now I just need to graph those points. So I'm going to come down here. I have 6, negative 12, which would be located right here. That's A prime. B prime is at negative 6, negative 12. So, gosh, this is jacking with my eyes. There, B prime. C prime is negative 6, negative 6, which is right here. And D prime is right here. Now, I multiplied times a negative number, right? My object got larger or smaller? It did get larger.
Because the absolute value is greater.
Because the absolute value of negative 3 is still greater than 1. So it is an enlargement. It's still an enlargement. Did it maintain orientation? It did. Its position on the, remember, the position is the same. Did it maintain congruence? It did not maintain congruence. Leilani?
How did you put that? You mean,
How did I get the scale factor of negative 3?
you just made it.
I made it up.
This is not congruent.
Yeah, that's okay. It did not maintain, did I say it did?
No, you said congruence is not the case.
Oh, yeah, okay, the sides maintain congruence. Thank you, very good. Is it an isometric change?
No.
Thank you. Yes.
If you were to find the scale factor of those, how would you do it?
You divide them.
You will do negative 6 divided by 2.
Oh,
They have to give you either the scale factor or they have to give you the 2 points. They can't say, here are my original points, what's the scale factor? Because there's nothing to find it with, right? They have to either give you the first and then the transformed points, or they have to give you 1 point in the scale factor. Could they give you these guys in the scale factor and have you work your way backwards? Yes, they could. They absolutely could do that. And we will. Okay? Any questions on dilations? Make sense? Dilations, remember your eyes. Dilations, bigger or smaller. Dilation is going to either become larger or smaller, unless the scale factor is 1 or negative 1. Any questions on that? Yes, sir.
So if you're multiplying by a negative number, will it always go down and
Yeah, it ends up, yeah. But basically what happened, like if you had done this times positive 3, it would have ended up like this. up like this, 1, 2, 3, 4, 6, 6, something like that. What would we do? 6, 12, no, we'll do that. 3, yeah, it would be, oh, I see what I did. Oh, it would have started at 3. Yeah, it would have done like this to this, to this, to this, to that. It would have done that.
Yeah, it would have been.
Basically what it means, you know what the origin is, right? If you multiply it times a negative scale factor, it ends up enlarging or reducing over the origin, across the origin. If it's the same value, it just moves kind of away from the origin. Okay. Okay, let's talk about rotations. Rotations get a little bit more complicated. Everybody good at dilations? Yeah. Okay, rotation. Let me go back to our little trick word. By the way, I never figured out how to do this. R-O-T-A-T-I-O-N. A rotation is a turn. A rotation is a turn. It's like the Earth rotates on its axis, right? A rotation is simply a turn. Now, in like 6th grade math, and even to some degree in 7th grade math, they just talk about something turning. Like they would say, okay, so that would represent a rotation because the R turns. We don't do that. Ours gets a little bit more complicated. Okay? And rotation is more mathematically defined in the 8th grade. That's what I want to talk to you about today. And we're going to practice with our coordinate grid. Alex, not using a calculator. Thank you. Okay? So I'm going to give you the rules, and then we're going to practice the rules. Here's the way that it works. Number one, well, let's kind of just go to a coordinate grid. How many quadrants are there in a coordinate grid? There are 4 quadrants.
Hence the name.
Hence the name quadrant. How many degrees are in a full circle? 300. Yeah, 360.
90.
It's okay, Cameron got it on the third guess. There are 360 degrees in a full circle, which means that each section of our coordinate grid represents how many degrees? Each section represents 90.
I'm saying, like, I'm not the only one. Each section is a square.
Okay. I don't know if that has to do with what I'm talking about, but yes, you're right.
So each square is 360.
And Queen Elizabeth is a lady. Right? Yeah, that has to do with math. Okay. I know you're going to hurt yourself. Okay. Which means that if we talk about our circle, then each section of the entire thing at 360 degrees, which makes each section 90. We have 90 degrees here. This will basically represent 180 degrees in our turn. This is 270 degrees in our turn, and we end up with 360. Now, the reason that's important is rotations can do one of 2 things. Rotations are kind of interesting. Number one, oh my goodness, we don't use left and right because that would be for an elementary school person. What we use are the terms clockwise and counterclockwise. A rotation can either be counterclockwise, which is the one that I drew on the board, or it can be clockwise, which will be its opposite. So they can either go clockwise, or they can go counterclockwise. There's a very, very important differentiation. Because if you're doing a 90-degree rotation counterclockwise, that is not the same as a 90-degree rotation clockwise. Now, interestingly, a 90-degree counterclockwise is the same as what counterclockwise? 270.
I knew it.
It's so full of garbage sometimes. That's good. I knew it. I just guessed that 17 times wrong, but I knew it. Okay. So, rotations. Now, here's the interesting thing. A rotation, if they don't tell you which way, it's assumed to be counterclockwise. That's a very important thing to understand. If they do not tell you specifically which direction, it is assumed to be counterclockwise always. So if I write down R 90 degrees, then I'm telling you that is a 90-degree counterclockwise rotation. Which basically means that an object that is here is going to move here because it moves 90 degrees or one section counterclockwise. If I take that same object and I'm going to rotate it 180 degrees clockwise, it moves 2 sections and lands in the other quadrant. Brendan?
How do you know, like, I don't really know how to ask the question. It's just like, how do you know that it would go that way?
Because I just said, if I don't tell you which direction, I said it assumed to be counterclockwise.
Okay.
What's the opposite way of a clock? This way.
Counterclockwise.
Counterclockwise. Okay, Jackson.
So, you're not able to rotate a shoe? Like, you can't.
Oh, you can, yeah, we're going to get to that in just a moment. I first need you to understand directionally which way we're going.
I'm confused.
Levine?
So, whenever you say all the time you do counterclockwise, what they change the points to negative x?
No, we're not dealing with points yet. I need you to just understand directionally which way we're talking about. We'll get to it. We'll have the order pairs work in just a moment. So basically, we have quadrants 1, 2, 3, and 4. Does everybody remember the trick on how to label your quadrants?
C.
Capital letter C. Good. So if I have an object in quadrant 2, and I rotate it 90 degrees clockwise, I want you to raise your hand, and I want to float it out, please. 90 degrees clockwise from quadrant 2, it would be in quadrant, Bennett?
1.
It would be in quadrant 1, because it would move 1 section over. If I have an object in quadrant 4, and then it's going to rotate 270 degrees. In quadrant 4, it's going to rotate 270 degrees. Brendan?
3.
It does end up in 3, because it goes 3 sections counterclockwise. Even though I didn't say counterclockwise, it's assumed to be counterclockwise. Leilani?
Why wouldn't you count, like, whatever it says every night?
When you're counting your steps, so I'm going to count my steps, right? Do I go 1, 2? Huh. So you count on the step. So if you're here, you don't count 1 section until you move it. It's counting steps.
1.
Okay. All righty.
3.
Now, here's where it gets interesting. Here's where it gets a little bit confusing. There are rules associated with what happens when something changes. And this is where you're going to use your graphs. So the first thing I want you to do is I want you to take your coordinate grid, and I want you to put a point at 2, 3, 2, 8, and 6, 8. So A is located at 2, 3. B is located at 2, 8. And C is located at 6, 8. Now, once you go on your coordinate grid, I want you to make it fairly dark, at least just the points themselves. I want you to make it fairly dark, the points themselves. Well, Alex, I said, as you come in, make sure you're prepared, and that was going to determine whether I needed to reprint it. Hold. Oh.
Anyone else needs more? I do. I use mine.
What?
I use mine for notes.
Okay.
I'm writing like
Got it, hold.
what? Oh my gosh, mind blown. You should just use this for your phone and make this orange.
Yeah. It gets in there.
No, it's not.
No, but the score isn't good. It's easier to write up.
It's smart.
Alrighty. Now, how many are going to need extra coordinate grids? Raise your hand. All right, if you need them up here. Now, let me first describe for you the way that the rules work. And it's going to look confusing until we do an exercise which we're going to do in just a moment. Okay? No.
No.
not at all. That has good geometry.
Oh.
Okay. So let's first we're going to talk basic counterclockwise, and you can then use what you know to kind of do the clockwise stuff too, because then you can just kind of figure out what it applies to. Let's assume that we are rotating the point x, y. Let's assume that we are rotating the point x, y. We have 90, we have 180, and we have 270 degrees. Okay? Oh my gosh, please do not ask about 360 or I will throw something at you. Now, here's where you need to pay attention or you're going to get confused. When we're moving the point xy, and we're going to move it counterclockwise, if it's 90 degrees, it becomes negative yx. If it's 180, it becomes negative x, negative y. And if it's 270, it becomes y, negative x. So I would like you to please write that down somewhere.
Wait.
Don't speak, just write. You move it 90 degrees, it becomes negative x, negative yx. If it's 180 degrees, it becomes negative x, negative y. And if it's 270 degrees, it becomes y, negative x. I'm going to explain or show you what that means in just a moment. I want you to write those rules down. Again, as I just stated twice, just write them down, and I'm going to explain it in just a moment. Is it an order pair? Okay.
Oh, I see why.
Now, here's what I would like for you to do. It's going to take a little bit of explaining. I want you to take the blank white piece of paper that you have. And you don't need very much room, but here's what you're going to do. You're going to put it on top of your coordinate grid, and you have to do two things. Number one, I want you to go to the center where the x and the y axis cross, and I want you to make that little cross so that you know where the x and the y are. It's basically going to look like a cross. That's in the center. Then you are going to trace through, and sometimes you might have to hold it up the light. You're going to trace through, and you're going to draw your points A, B, and C on the white piece of paper through it. Okay? I'm going to turn the lights on so I want you to look through, and then we'll turn it back off. So again, I want you to, listen, I want you to, through that white piece of paper, draw where the origin is, which is an x and a y axis, a little cross, yes? Then put it back on carefully so it's exactly where you need it to be. And you're going to also trace your 3 points A, B, and C. You're going to trace your 3 points A, B, and C. Nancy, what's for me? So this is what your white paper should look like. Now, what I would like you to also do, please go ahead and label A, B, and C so you know where they go. Label the points A, B, and C. Okay? Make sure it's exact. Now, okay, so you should have a cross on your white paper. So you got it? And perfect. Now, here's what you are going to do. You are going to take just the white piece of paper, not your coordinate grid, and you are going to rotate it or turn it 90 degrees. You're going to reset up your cross at the origin, and you're going to write down where those 3 ordered pairs go.
Whoa.
You are going to turn the white paper 90 degrees, which rotates your image, one section. And then those points will end up on other points. And you're going to write down the ordered pairs for those points, please. If you need help, just get with the neighbor or call me over and I'll talk to you about it. But basically, you're just turning it one section. Remember, we're going counterclockwise. So you should have turned it counterclockwise. Okay. Okay. No, no, just write down what you think those ordered pairs are. I will tell you where I am pretty sure that each ordered pair went. And see if I am right.
Oh, that's good. I didn't get that. I rotated the paper in the right line.
Counterclockwise.
Counterclockwise.
I got
One
that.
section.
And it ended up in the fourth quadrant. Well, that's
There's no way in the world, Alex, you rotated this counterclockwise and ended up in quadrant 4.
I rotated the white paper.
Right, which is
Alex.
left.
Yeah.
Alex, did you rotate your white paper this way? Here, hold it. Let me see.
I rotated it.
Okay, so now rotate it.
Even
So yeah, so right now, you're in quadrant 2.
wait. It began here. And I rotated it here.
Right. So now where is it? No. Yeah, you're in it. Now, here's how it works. Has anyone now figured out how the rule works? So if you look at the rule I just told you, the xy, if it's 90 degrees, should have become negative yx, correct? Which means that for point A, the x and the y switch places. And the first number becomes negative, so it actually went to -3, 2. The x and the y switched on the B, so it went from 2,8 to 8,2, but the first number became a negative, which is why it's negative yx. And the C went to negative 8,6. That's how the rule is applied.
That's so strange.
Another way to talk about it, because a lot of times the x's and the y's get a little bit confusing. Here's another way to think about it, guys. Go back to my rules really quickly. Okay? There are basically 2 rules you need to think about. Number 1, if it's 180 degrees, the ordered pairs stay in position, they just both become their opposites. The ordered pairs stay in position. So if I'm rotating the point -3, 2, 180 degrees, what does it go to? 3, -2. Both of them simply stay in position but change to their opposite values. That's the negative x, negative y.
You're running 270.
Okay, no, just let me do it. I'm better at this. I'm not going to call on you. I'm not going to call on you until I'm going to talk. Okay? Now, on both the 90 and the 270, the x and the y change positions. On both the 90 and 270, they change positions. On the 90, the first one changes value, and on the 270, the second one changes value. So on the 90 and the 270, they both switch, no matter what. But on the 90, the first one changes its value, and on the second one, on 270, the second one changes its value. Okay? Which means if I'm rotating, let me get to a blank. If I'm rotating the point 6, -4, 6, -4, and I'm going to rotate it 270 degrees counterclockwise. Jackson, where does it go?
-6. No. 4, 6.
No. Let me tell you why hurrying's fast. -4, -6, because they switch, and when they switch, it becomes -4, +6, but the second one becomes a negative. So now it's -4, -6. It goes right there. It rotated 270 degrees counterclockwise. Okay? Told you it was going to be harder. It's kind of interesting as long as you get the rules. Make sure you keep the rules. Okay? Any questions on that? Yes, sir.
But how does the rule apply then?
This is a 270-degree counterclockwise rotation.
Yes, and on your thing it shows what changes.
It shows that xy went to y negative x, which it did.
What is x negative?
The y became the x guy.
And y to the x and then
Exactly.
and then the x becomes a negative.
But since the
y was a negative,
Yeah. Yes. Leilani?
Since 4 is already negative, it keeps the same value.
Yeah, never changed.
Right? So it doesn't have negative signs, but the same value.
Yeah, negative doesn't really mean, well, it sort of means negative. It really means the opposite. Opposite's a better way to think about it. Okay? Any questions on that? So what is a dilation, basically? Enlarging or reducing a figure. A dilation is enlarging or reducing a figure. A rotation is basically a turn. It's just kind of a complicated term because whereas before, you got to turn these lights off.
We're in the movie theater again, guys.
Okay. So you have one worksheet. You may work together. Good luck. Let me get